Okay, so let's continue. So on functions, but I guess we will need functions here to be continuous. So this will be the inner product. By the way, we cannot do this using summation, and the reason is that summation of uncountably many positive numbers, no matter how small they are, is always infinite. Okay, uh, so it's because of uncountability, yani o George Cantor'un yaptığı işlerden dolayı. Dolayısıyla böyle tarif etmek zorundayız. Okay. Yani Newton'un integrali e, keşfetmesi o anlamda önemli, ama hani muhtemelen Cantor'un yaptığı işleri tabii ki bilmiyordu. Hani okay. So the fact is that let's write as a proposition. The formula f g equals minus L to L f of x times d of defines an inner product on the vector space of continuous functions on minus L. Onu şöyle gösterebiliriz. Yani continuous functions minus L. Tamam mı? İspatı, bunu muhtemelen linear algebra'da yapmışızdır aslında, ama yapalım. Ne göstereceğiz? It should be linear with respect to both components, and it should be positive definite. So linearity comes from this f1 plus f1 plus f2 g is what? Well, this is integral minus L to L f1 plus f2 x times g of x dx. But by the properties of integral, this can be written as f1x times gx dx plus minus L to L f2x gx dx, and that is just f1g plus f2g, And similarly, okay, also this gadget C times F G, where C is any, let's say, real number, is what? So this is minus L to L, C times Fx, G of x dx. But this C goes out. So this is C times Fg. Okay? So it is linear with respect to the first component. Similarly, it will be linear with respect to the second component. Okay. Similarly, f g1 plus g2, this is just f g1 plus f g2, and f t times g is just t times fg. Okay, for all c. What else? We have to show that if one of them is zero, yok, ona gerek yok. Zaten pozitif definitely f çarpı f şeydir. F times f. This should be positive. Let's see. This is just this gadget. So this is just f square x, and this is a non-negative function. Therefore, this integral will be positive. And if it is zero, now assume f is zero. Ne göstermemiz lazım? Must show f is the zero vector. Okay. How can we show this? Well, we can show it this way. Şu fonksiyonu tarif edelim. Let h of x to be the following. Yok, h of t şu olsun. Sıfır, pardon, eksi l'den t'ye kadar f x square dx. Tamam mı? Şimdi şunu biliyoruz. Zero is equal to minus L to L f squared x dx. This is a positive function, non-negative function. Therefore, okay, I can write it like this. Minus L to t f squared x dx plus t to L f squared x dx. This is just h of t. And what about this? Well, whatever it is, this is always non-negative because this function is non-negative and you have some integrals, so this is non-negative. Therefore, this thing is non-negative, so if I erase this, I get something smaller. So we have this. And of course, this gadget is also positive. Okay? So means what? 0 is less than, greater than this, and this is greater than 0. Therefore, this h of t is just the zero function, 0 for all t. Değil mi? Well, if it is 0, then its derivative must be 0. Okay. Since ht is 0 for all t in minus L, we see that h prime t is 0 for all t. Well, what is h prime t? ht is this. So h prime t is just, by the fundamental theorem of calculus, this is just f squared t, right? And this is 0 for all t. So it implies that f of t is 0 for all t. Okay? So f is 0. So this finishes the proof. Okay? But here, of course, we are using the fact that f is a continuous function. Otherwise, this formula, you cannot use fundamental theorem of calculus. Değil mi? Yani şu fonksiyonu alın. Değil mi? Bunun integrali 0 ama kendisi 0 değil. Yani o yüzden hani fundamental theorem of calculus continuous fonksiyonlar için anlamlı. Tamam mı? So we have this inner product on this vector space of functions. Okay. Dahası şunu görmüş olduk. So you see, we have this three computations. So this shows that inner product of these two functions is always 0. Inner product of these two functions is 0 if they are different. And again, inner product of these functions are 0 if they are different. Therefore, all these functions are orthogonal, right? Inner product of any two of them, distinct functions, is 0. So this collection of sines and cosines is an what? Is an orthogonal set. They are not orthonormal because you have to have one, not L. But note that the collection of functions, which collection? Cosine m pi x over L, sine m pi x over L, m from sıfırı da katabilirim. Sıfırı katarsam 1'i elde edeceğim. Sıfırdan sonsuza kadar. Tabii sıfır koyarsam bu 0 oluyor ama bu 0 değil. Bu 1. O da diğerlerindik. Is an orta normal set. Orthogonal set. Şurada şeye dikkat edin. Remark. Cosine 0 pi x over L is just the constant function 1. Okay? Yani m yerine 0 yazdığım zaman sabit fonksiyon elde ediyorum. Okay. Yani isterseniz onu hatta şöyle yazayım. Bu küme nedir? Bu küme şu. Sıfırı yazmayalım. 1 var. Kosinüs x sinüs pardon sinüs pi x pi x over L sin pi x over L cosine 2 pi x over L sin 2 pi x over L cosine 3 pi x over L sine 3 pi x over L, and it goes till infinity. Okay, so this is an orthogonal set. Okay. In this inner product, the norm of a function f is given by norm of f. Nedir norm? Inner product'ın karekökü değil mi? Yani şu minus L to L f squared x dx, and then we take square root. Okay. Okay. Given a function integrable olsun. Integrable. Yani continuous olmak zorunda değil. On minus L define şunları tarif edelim. A n to be 1 over L minus L f of x cosine n pi x over L dx. Burada n büyük eşit 0. So n is any integer larger than or equal to 0. And bn 1 over L minus L f of x sine n pi x over L dx. Here I assume n is at least 1 because if you plug n equals 0, this is 0, okay? Okay, then the series, then the infinite series, şu seriye bakıyoruz. 1 bölü 2 tane A0. Ondan sonra n birden sonsuza kadar an cosine n pi x over L plus bn sine n pi x over L. So this series is called the Fourier series of f of x. Okay. Bu tabii neye denk geliyor? Yani aslında lineer cebirde bir elemanı ortonormal basis elemanları cinsinden yazmak, değil mi? Bu isterseniz şöyle yazayım. Remark diyelim ki if E1 En is an orthonormal basis for an inner product space, then for any vector v we have, değil mi? V vektörünü şöyle yazabiliriz. V vektörü işte AI A1 E1 AN EN şeklinde yazılır. Where AI is just the inner product of V with EI. Değil mi? Eğer ortonormal bir basisiniz varsa her vektör bu şekilde yazılır. AI'da AI is just the inner product. Why is that? Well, just take the inner product of V with EI. So you will get E inner product with V, and inner product of EI with this will be just AI, because inner product of EI with E1 is 0, with E2 is 0, with EI it is 1, all others are 0. So inner product of EI with this guy is AI, and inner product of EI with V is just this. And that's the basically the same, idea. We just take inner product of f, or with all the functions, this orthogonal set. Our set is not orthonormal. These functions are not orthonormal. They are orthogonal, meaning that they don't have length 1. They have length actually uh, square root of L. Çünkü normu they have norm L. No, norm squared is L. Therefore, norm is square root of L. But this one, yani şuna bakın. Inner product of cosine n pi x over L with cosine n pi x over L. This was L. Therefore, norm of cosine n pi x over L is just square root of L. Okay? And similarly for sine. But inner product of 1, integral of 1 times 1 is 1 over the interval 0 to, no, minus L to L. So this is 2L. Okay, 2L. Therefore, norm of 1 constant function is just this. That's why, here we have this 1 over 2 for A0, but for these ones, we don't have that. Here, of course, I am not claiming that this is equal to f of x. Okay, here in a finite dimensional vector space, if we have an orthonormal set, orthonormal basis, then we know that v is equal to this one. But here, now I am not claiming that f is equal to this gadget. Okay, but we will see that it is the case under some conditions. Not always, but sometimes. Fourier serileri yani PD'lerde işte kullanılıyor. Applied matematikte, mühendislikte çok kullanılıyor. Hatta yani günümüz mühendisliğinin herhalde yarısı bu Fourier serileri falandır yani. Efendim? Ee, eşit değil ya. O discontinuity'lerde biraz sıkıntı vardı sanki. Neyse göreceğiz. Şey yapacağız zaten. Evet. Yani onu teorem olarak göreceğiz. Her zaman doğru değil de koşul var. Okey. Şimdi örnekler yapalım. Let's find Fourier series. Let's compute the Fourier series. Fourier series . of some functions. Okay. Let's do, for example, -1. Okay. Yani isterseniz tabii şöyle de yapabiliriz. Ne bileyim, şöyle diyelim. Pardon. So what is this function? So it is defined on minus pi and pi. So our L is, let's say, pi, and the function is 0 up to 0. No, -1 up to 0. -1. And from this point to here, it is 1. So let's find the Fourier series of this gadget. What kind of function is this? This is an odd function, right? Efendim? Ha, evet, şöyle diyelim. Haklısın. Şöyle yapalım. Hatta şuralarda da 0 yapalım. Ki şeye de extend it. So it's like this, and 0 if x is 0, pi or minus pi. Okay. Tamam. All right. Note that f is an odd function. Uh, thus uh, an, let's say, what is this? Inner product. So an neydi? 1 over L times minus L f of x cosine n pi x over L dx. Well, no matter what n is, this is an even function, right? But this is an odd function. So the product is an odd function. And the integral of an odd function, of course, is always 0. So an's are always 0. Okay. What about bn? Well, bn is just 1 over L minus L to L. Okay. F of x sine n pi x over L dx. Well, actually, L is just pi, of course, in our case, minus pi to pi. Now, this time, actually, we can make, ya şöyle yapabilirim. We can make a simplification. What's that? Well, this is odd. This is odd. The product is even. Therefore, this is an even function over a symmetric interval like this about the origin. So this is just 2 times the integral from 0 to L f of x sine n pi x over L dx. Okay, so we can make a simplification like this. Değil mi? Even fonksiyon integrali. İntegralin sadece tek yarısını alın. İşte sağ yarısını. Oradaki şeyin 2 katı olacak. Peki. Let's compute that. So Bn is just 2 over pi 0 to pi. Now what about f from 0 to pi? Well, f is just 0 to pi. It is just 1. So f is just 1. 1 times sine n pi x over pi dx. So this integral is just 2 over pi. Integral of sine is just cosine, but minus, right? Minus pi over n pi. Yani x'in katsayısı aslında 1 bölü n, yani başka bir şey değil. Cosine n pi cosine nx. Pi yazmaya gerek yok. Pi's are cancelled, right? So 0 to pi. So these are cancelled, of course. So minus 2 over n pi. And then cosine n times pi minus cosine 0. What is cosine n pi? If n is even, then it is 1. If n is odd, it is minus 1. So this is just minus 1 to the power n, right? So Bn is just, and this is always 1. So if n is even, then this is 1 minus 1, it is 0. If n is odd, this is minus 1, this is minus 1, minus 2, another minus 2, so it is 4. So we have 4 over n pi if n is odd, and 0 if n is even. Okay. So what is the Fourier series of f? Hence, the Fourier series of f of x is what? Şöyle yazı. Notasyon şu. F of x has the Fourier series a0 over 2 plus neydi işte n from 1 to infinity an cosine n pi x over pi, ya da L yazayım, tamam, şöyle. Önce plus bn sine n pi x over L. So what is this? This is just a0. An'ler zaten hep sıfırdı. I have only bn's and the odd ones. So this is just n from 1 to infinity but n should be odd, and then bn, and bn is just 4 over n times pi, and then sine n pi x over L. İsterseniz bunu şöyle yazabiliriz. N birden sonsuza kadar, ama sadece odd number'lar olacak. So I can just replace n with k from 1 to infinity, 4 over 2k minus 1 pi sine 2k minus 1 L is pi, so L is pi nx. Böyle yazabiliriz. Değil mi? Sadece odd. Since I am summing over only odd integers, I can replace n with 2k minus 1, k from 1 to infinity. So 4 over 2k minus 1 times pi times sine n pi x over L. Pi's are gone. N times x, n is just 2k minus 1. So this is the Fourier series of f. Well, you may think that, this function was much simpler than this, right? I mean, this is an infinite sum, and you represent a simple function with an infinite sum. So this may look not efficient, but the thing is that you can apply this to any function, and the nice thing about is that you represent function by a sequence of numbers, just a-n's and b-n's. A function, has uncountably many values, so you cannot just list the values of a function unless you know its formula. You cannot represent it correctly, but here, via this theory, you can represent any function by an countable set of numbers, namely a-n's and b-n's. Okay, that's the power of this Fourier transform or Fourier series. Yes. Tabii ki. So here I wrote it this way because bn's are this if n is odd, but when they are even, it is 0. So half of the series is gone. Therefore, you either write it this way, and from 1 to infinity, but you have to say that n is odd. You have this, or odd integer is just 2k minus 1. You just plug that expression here. Tamam mı? Şu. L, ama L P'ye eşit ya. Okay, so yeah, we did one example, and actually, okay, so next time I can do one more example, and then we will see the Fourier convergence theorem. So when this series converges to f of x. Here we write it like this. This doesn't mean that this is equal to this gadget. So this is just the Fourier series of f, but we will see when they are equal.